Okay, we're going to talk about nuclear chemistry. And in nuclear chemistry, there are three types of radiation. There's alpha, beta, and gamma. The first one is alpha. Alpha radiation is a helium nuclei that has been emitted from a radioactive source. So you're going to have the nucleus of a helium that's being spit out of another radioactive atom. It's going to have 2 protons and 2 neutrons. So that means it's going to have a double positive charge. It's going to have a 2+ charge. It can either be written as the Greek letter alpha or as a 4,2-He. We're going to use this when we're doing reactions. This 4 should be directly over the 2, but because of Microsoft typing, you can't put the 4 directly over the 2. Alpha particles are not very penetrating. They can be stopped with a sheet of paper or your skin, so this is going to help contribute to your melanin darkening, sorry. So if you look, here we have radium. Radium is atomic number 88. That's going to break down. It's going to give us a radon, which is atomic number 86, and our helium nuclei. Helium is atomic number 2. These numbers at the top are the mass numbers. So this particular isotope of radium weighs 226 AMU. This particular isotope of radon weighs 222 AMU. And if you add these two numbers together, because you're adding these two particles together, to get this guy, think of this as an equal sign. 222 plus 4 equals 226. And the bottom numbers do the same. 86 plus 2 equals 88. So if you have 2 particles, you can figure out what that third particle is going to be. Next is beta radiation. In beta radiation are fast-moving electrons formed by the decomposition of a neutron. So this neutron is going to break down. They're neutral. And it's going to give us a proton, which has a positive, and an electron, which has a negative charge. Negative and a positive make a neutral. This neutron is going to decompose into a proton. Proton is going to stay in the nucleus, and the electron is going to go flying out. Beta particles have a negative charge and virtually lack mass. It can be written as the Greek letter beta or 0, -1e. Electrons have a -1 charge and they have no mass. Again, the zeros should be directly over the -1. These guys are really bad. They're called free radicals. They are much more penetrating than an alpha particle. It's going to take something a little bit more dense, like aluminum foil or a thin piece of wood, to stop these guys. They're going to go deeper into your skin tissue to cause more damage there. And the same thing that applied to alpha is going to apply to beta radiation. Both sides should be equal. So if our electrons over here, because remember it broke down into this, 137 plus 0 equals 137, and 56 plus a -1, that's the same as subtracting 1, gives us 55. So both sides of our arrow are equal as far as mass and atomic number. And the third is gamma radiation. So this is the Greek letter gamma. Looks kind of like a upside down ribbon or a fish swimming down. It's going to be a high energy electromagnetic radiation. It's often emitted with an alpha or a beta emission. And gamma rays have no mass. They have no electrical charge. So they're not going to alter our atomic mass or number. They're just going to be there. So I certainly will not expect you to be able to identify when a reaction emits gamma radiation, but I do expect you to understand what it is. So gamma rays are going to pass easily through wood, paper, the human body. They're very similar to an X-ray. They can be stopped by several centimeters of lead or several centimeters of concrete. I want you to think about the difference, why it only takes centimeters of lead and meters of concrete to stop this type of radiation. So gamma radiation, here we have cobalt-60, that's our what we're starting with. This guy's going to emit a beta particle, an electron, so we're going to get some nickel, and then the gamma radiation is also going to be emitted. So it's not factored into the equation because there is no mass and it has no atomic number.